Here's the 50. You can see the pinouts on the back. And on the front, here's what it looks like. This pot is for adjusting the duty cycle of the square wave. You get an LED on there, you get the actual chip, and you get an oscillator on the side. You can get a square wave that is adjustable. Or you can get a sine wave. On the datasheet are a couple things to note. 51 goes up to 180, although it's advertised for 70, and 50 goes up to 125, it's advertised for 40. The reason for this difference is that there are filters on the board that this sheet here does not take into account. Power used versus the 51 is slightly higher over here, and these things can change their phase as well as frequency. The 51 can do increments of 11.25 degrees, and the 50 can only do these discrete steps over here and 11.25, or combinations thereof. Now this 50 also has a 0.0291 Hertz resolution, while the 51 has an 0.04 Hertz, which is slightly less resolution. You might want to take note of a couple of things. Mostly it's this stuff. How long does it take to set a frequency? Output impedance here, 120 kilo ohms, although that doesn't match what the board is because, again, there's stuff after this chip. And really, that's about it for the data sheets. On the table are the two modules that I've been talking about. On the left is the AD9851, and on the right is the 9850. These boards look exactly the same, the chips are different, and the oscillator frequencies on them are different. Now if you look over there, that is the Arduino Pro Mini that is driving these two modules. It's sending the commands over to tell it which frequency to change to. And this thing is running at 60 megahertz, and it's the 5-volt version. Now this took a little while to set up because, as advertised, pinouts really never correspond to what they're supposed to correspond to. So when they talk about the data pin, there's a pin labeled data underneath here. They're not actually talking about that, they're talking about the digital 7 pin. Now on the computer, I've programmed the microcontroller to do a couple things, and you can see that it's actually fairly simple how I did it. So let's look up at the computer real quick. Here you can see the code. I just took someone else's code, or two of them anyway, one for the 9850, which you see there, and then the 9851, which is a bunch of this stuff, and I tossed them together and then made a small block here that just calls the two libraries or blocks of code up there. What this does right now is, if you look over here, if I type in a prefix of 1, this is going to set the 9851. If I type in a prefix of 0, it's going to set the 9850. And if I do 0, say 300, well, that's going to set the 50 to 300. If I do 1 300, that's going to set the 51 to 300. And if I want to set both to, say, another frequency, I could do 2, and then, change the frequency to 600, and they'll both be set to 600. Right now we're looking at the traces for the 9850 here on top, and the 9851 here on the bottom. Now, this 9850 is kind of a bit fat with the line, because I've probably done something to it. Right now, if you touch the output in any way, if you unplug a wire, plug a wire in, the signal disappears and you're left trying to figure out what went wrong, and it's kind of a random chance of fiddling with the commands, resetting the thing, and sometimes you'll get the output back, sometimes you won't. So right now I have it and I'm not going to touch it. These waveforms essentially agree on what is roughly 500 Hertz. That's what both of these are set to at the moment. And I can continue setting this to a slightly higher frequency, so I'm going to set both to, say 1000 Hertz. So there it is, 1000 Hertz. And Yeah, let's fix the triggering. There we go. And you can see that it is essentially still pretty good. They line up right where they're supposed to, except that you get a little bit more squiggle and fuzz on top than on the bottom. That's no problem right now, but let's keep going. That was 1,000, let's go to 10,000. That's I'm entering 2, 10, 0, 0, 0. Okay. Still pretty good, right? The top one got slightly fuzzier. Essentially they're still lined up with each other, and I'm triggering on the top channel right now, and it looks like the bottom is staying still also. So far so good. Now let's keep going. 100,000. And right now you can see that this bottom trace is starting to very slowly drift over a little bit. So at 100,000 hertz, 100 kilohertz, the frequencies of the modules are just slightly different, and this is not anything significant right now. The bottom is marching past the top at, less than 1 hertz. So right now we really don't care. It's the same thing. Now let's keep going to 40 meters, which is what we're trying to play with right now. So that is, let's go 7055 000. And here you can see that the frequency difference is actually a little bit more significant. If I change the triggering to channel 2, you can see that the top trace marches past the other way, and if I change it back to channel 1, this trace starts going that way again. And this is again still within a couple hertz of each other, no problems, but this can be something to watch out for when you're actually playing with the two modules hooked up to a circuit you're testing. And you can see that their voltages are actually just about the same also, and that's interesting. When I popped on the voltage cursors, started shifting around, but yeah, we're getting a little bit over a volt. Let's change both channels, move them up a little bit, and yep, we get a little bit over a volt for each channel. I'm going to be using these synthesizers in the next segment, so hopefully these modules make it until then. Hopefully I don't blow anything else up, and I will see you in the next segment.